This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on vertical asymptotes. So we're going to look at various rational functions and decide where the vertical asymptotes will be. So the first example is f of x equals 1 over x minus 3. It is a rational function because the numerator is a polynomial, 1. The denominator is a polynomial, x minus 3. So to find a vertical asymptote, what do we have to look for? We need to find out when the bottom is 0. So the bottom currently here is x minus 3. Remember, you cannot divide by 0. Mathematics does not permit us to divide by 0. I hope you know why. So if that's the case, when is the bottom 0 is what we're going to look at. And we're going to take a look at when is x minus 3 0, and of course that would be when x equals 3. So there should be a vertical asymptote for this function when x equals 3. Let's take a look at the picture. So here's a graph. We have a horizontal asymptote, which is the x-axis. Y equals 0 is a horizontal asymptote because the degree of the bottom is greater than the degree of the top. It's a bottom-heavy fraction. Vertical asymptote is here at x equals 3. So you'll notice as we get closer and closer to 3, these functions are asymptotic. They're either going to minus infinity or plus infinity, growing in that direction. Here's our next example. We have 5x plus 2 over x squared minus x minus 12. This is a rational function. Numerator is a polynomial, 5x plus 2. Denominator is a polynomial, x squared minus x minus 12. What do we need to look for? We need to find out when is the denominator equal to 0. But let's factor that. X squared minus x minus 12 would be x minus 4 times x plus 3. Now, determining when that's 0, factoring x minus 4, x plus 3. So x minus 4 is 0 or x plus 3 is 0. Solving here, adding 4 to both sides, x is 4 or x is negative 3. You'll notice that makes the bottom 0. So that gives you an indication that could be a vertical asymptote. You've got to make sure that the numerator is not also 0. So if you plug in 4, the top's not 0. You plug in negative 3, the top's not 0. So indeed, we have a situation here where that will be vertical asymptotes both at x equals 4 and at x equals negative 3. If the top and the bottom are both 0, then it's not a vertical asymptote. That will give us a hole. We'll talk about that in a later example here. So x is 4, x is negative 3. Those would be the two vertical asymptotes for this problem. So you can see there's the vertical asymptote for x equals 4. Vertical asymptote for x equals negative 3. Two vertical asymptotes for this, and you can see how this behaves. Now, if you're going to graph this, you need to sort of choose some numbers near the asymptote so you get a feel for the direction that they're going. So graphing it by hand is still fairly challenging. You've got to choose quite a few points to get a feel for the direction that these various pieces are going. So let's look at this example. We have a quadratic on top, a quadratic on the bottom. Polynomials in both positions. So this satisfies our requirement for a rational function. We're looking for vertical asymptotes. Vertical asymptotes are identified by finding out when is the bottom equal to 0. So looking at this, factoring the top, x plus 4 times x minus 1 is x squared plus 3x minus 4. X squared minus 6x plus 5 would be x minus 5 times x minus 1. Well, the bottom is 0 in a couple places. The bottom is 0 when this piece is 0. The bottom is 0 when that piece is 0. And you know we're not allowed to divide by 0. So if we're thinking of domain, x cannot be 5. And x cannot be 1. So the domain is all real numbers except 5 and 1. But you'll notice there's something funny happening with this x minus 1. This x minus 1 will divide out. So when that divides out, we just have x plus 4 over x minus 5. But remember, the domain is still everything except 5 and 1. It is not fair to plug 1 into this thing. Now, if we're thinking of vertical asymptotes, when is the bottom 0? When is x minus 5 equal to 0? Well, x minus 5 is 0 when x is 5. But what about this x minus 1 thing? Since it cancels out, it is not a vertical asymptote, but rather it is a hole. The graph is not continuous there. There is a break. 1 is missing. Whatever the y value is, 1 is missing from that graph. So the whole is when the x minus 1 cancels out. So x minus 1 is 0, x equals 1. Vertical asymptote at 5, whole at 1. That's our issue. So here was our function that we're looking at. We had the vertical asymptote and we had the whole. So what does the graph look like? What's going to happen? And before I do it, let's also think horizontal asymptote for a minute. The ratio of the highest power of the top and the bottom, ignoring everything but x squared over x squared, will give us a horizontal asymptote at 1. But vertical asymptote at 5 and a whole at 1. So let's see if we can identify that. A little hard to see the horizontal asymptote at y equals 1 because I didn't draw the graph that way. But you'll notice the whole here, when x is 1, we have a y value of negative 1.25. And there is your vertical asymptote at x equals 5. All right. We're going to talk about order 2 asymptotes versus order 1 asymptotes. If I have f of x is 1 over x plus 3, we know we can find a horizontal asymptote, check that a vertical asymptote, when the denominator is 0. So our picture looks like this. And you'll notice what we have here. We have 1 over x plus 3. We have a vertical asymptote at negative 3 because that makes the bottom 0. And then you'll notice how it is going up on one side, it is going down on the other side. That's what we call an order 1 asymptote because x plus 3 is only there one time. But if instead I had x plus 3 squared downstairs, so think about this. In this case, negative 2.9 plus 3 is a positive number. 1 over a small positive number is a large positive number. Negative 3 plus 1, negative 3.1 plus 3 would be a small negative number. 1 over a small negative number is a large negative number. But over here, no matter what you do, eventually you're going to square it so that the results are all going to be positive. If x is approaching negative 3, negative 2.9 plus 3, positive number squared is positive. Negative 3.1 plus 3 is a negative number, but when you square it, it's also positive. So what does the asymptote give us there? We get this sort of an asymptote. So it is growing in that direction. You'll notice in every case, everything is positive. So for an order 2 asymptote, you'll notice both pieces are heading in the same direction. But the fact of the matter is, this had to be positive. The 1 is positive, which enables it to give us all positive numbers. So x plus 3 is 0 is where the vertical asymptote is. So x equals negative 3 is indeed the vertical asymptote, which you see on both of these graphs, the order 1 vertical asymptote and the order 3 vertical asymptote. Now, how does it change if I have f of x is negative 1 over x minus 5 squared? So x minus 5 squared will always be positive. Negative 1 over a positive number will always be negative. This is an order 2 asymptote because x minus 5 is there twice. The bottom is going to be 0 when x equals 5, but in all the cases, the function should be tending towards negative infinity rather than positive infinity in this situation. So what is that going to look like? There we go. Horizontal asymptote at y equals 0. Horizontal asymptote is the x-axis because it is a bottom-heavy fraction. The degree of the bottom is greater than the degree of the top. So x equals 5 here is our vertical asymptote, and as we said, all of the values are negative, heading in that direction for an order 2 asymptote. And that will conclude this lesson.